Thank you, everyone. As the title says, I will be talking about submillimeter galaxies and how we can use them to say a few words about phenomenon of cosmic magnification. The results that I will show here are all contained in this paper here that we just submitted to Astronomy and Astrophysics. So let's start with a brief introduction on the field that we're working in, which is weak gravitational lensing, which is a field that studies the statistical correlations of both magnification and distortion effects due to gravitational lensing. It's become one of the most fruitful and useful pathways for cosmological analysis, thanks to the fact that it is sensitive to both kinds of matter, both baryonic and dark. And it's usually studied in the cosmological setting via two main observables. The first one is cosmic shear, which is this coherent pattern of ellipticities that appears within galaxies due to the large-scale structure. And the other one is galaxy-galaxy lensing. That is the correlation between the ellipticities of background galaxies and the positions of foreground galaxies. But there's actually a third observable that's usually overlooked as an observable itself, which is cosmic magnification. Indeed, if you cross-correlate the positions of both foreground and background galaxies that do not overlap in redshift, what you can obtain, if you choose your samples correctly, is a non-zero signal that's highly significant and which is entirely explained by the phenomenon of magnification bias. What is this? Well, we know that magnification due to gravitational lensing causes two effects that are in some sort of tug of war. On the one hand, it boosts the flux of faint sources, and on the other hand, it dilutes them away in some sense. It stretches the solid angle that they subtend in the sky, which means that when you compute the number counts of background objects, they will be modified with respect to the absence of lensing. On the one hand, they're increased thanks to this boosting of the flux, but on the other hand, they will be decreased thanks to this due to this dilution effect. And so the net result of these two competing forces is what we call magnification bias, and it effectively creates a mismatch between the observed counts and those that you would expect in the absence of lensing. Now, this effect can be actually quantified and measured by assuming that the foreground galaxies are actually tracing the underlying mass distribution, because you would expect this effect to happen around those foreground galaxies, but in the background. And indeed, when you cross-correlate the positions of foreground and background galaxies, what you're actually cross-correlating is the positions of foreground galaxies with the convergence field due to the large-scale structure. And this allows you to probe cosmology with this observable. It's also highly dependent on this beta parameter that we see here, which is the logarithmic slope of the number counts of the background sources. The steeper they are, the more significant this effect will be. And this is the reason why we chose submillimeter galaxies for our analysis. Submillimeter galaxies are very high redshift galaxies, which are extremely bright in the infrared, that are very strongly suppressed in the optical, and that have very large star formation rates. For our purposes, the interesting idea or characteristic is that they have very steep intrinsic number counts, that we can see in this blue line here that's very steep and drops up abruptly. The idea of why this is useful is that if you think about it at a fixed flux, the number of galaxies that can actually go over the threshold of detection with respect to the galaxies that were already there at that flux is much larger than for a regular galaxy with a very much moderate number counts. And the pictorial representation of the effect is on the right figure, where some galaxies that are too faint to be observed at a fixed detection limit, if they are around a certain angular distance from the foreground sources, they can be boosted enough so as to be included in our sample of background galaxies. So you will measure an excess of background galaxies around foreground galaxies with respect to what you would measure if there was no lensing effect. Now, this is the visual representation. Now let's dive into the details and see what we can do and say about everything. So first of all, our background sample of galaxies, as I've just said, is made up of submillimeter galaxies, for which we extract them from the Herschel Atlas survey, a far-infrared survey that observed the sky in 6 far-infrared bands, and which observed those 5 regions we see here, one in the North Galactic Pole, another one in the South Galactic Pole, and then 3 celestial equator regions called G9, G12, and G15. Now we want to choose those galaxies that are, of course, in the common area with the foreground sample that I'll just introduce in a moment. And we select those submillimeter galaxies from the survey by imposing a photometric redshift range between 1.2 and 4, and a 4 sigma detection at the 250 microns, which is about 29 millijansky. Regarding our foreground sample, we chose them from the Gamma spectroscopic survey, which is a highly redshift complete survey, which was kind of coordinated with H-Atlas for a maximum coverage of around 207 square degrees. And we chose those galaxies with spectroscopic redshift between 0.2 and 0.8. This is important because we want to ensure that there is no redshift overlap between the two samples, so as to be sure that the cross correlation that we measure is not contaminated by any autocorrelation of the signal. Now, with our 2 galaxy samples, now we want to measure this angular cross correlation via the usual or natural modification of the Landy-Saleh estimator for autocorrelations of galaxies. We basically measure the pairs of foreground background galaxies at a given angular distance, and then we compare with what you would get with random catalogs, both for the background and the foreground. The thing is, we have 4 specially separated fields in the sky, so there is no actually one way of doing all this. You could, for example, split each of the fields in smaller mini regions, like the one in red you see at the top, and then measure the cross correlation in each of those regions and average over all of them. This was actually the approach that was done in previous works along this line. But the size of those minimal regions, if you wish, can be subject to a measurement bias called integral constraint, which is not straightforward to correct. So for this work right here, what we've done is just a single sole measurement using all the available area, and then internal covariance estimation for the errors using bootstrap resampling methods. So you do that, and this is what you obtain. In black, we have our new data set, and in gray, I'm showing the results from the previous approach of González Nuevo et al. In gray. So the first thing we see is that the error bars are smaller at all scales, and that, of course, we can reach larger angular scales because we're not limited by the size of those minimal subregions that we defined earlier. Now, this data set is, of course, obtained using only a wide foreground redshift bin. We're not doing a tomographic analysis here. This is just for showing purposes. Now, regarding the physical model that we're going to use within the weak gravitational lensing regime, which we are in, we need to describe the correlation between galaxies and matter in the nonlinear regime. And so we use for this the standard halo model approach, where we describe the galaxy halo connection using a simple 3-parameter halo occupation distribution. In a sense, we say that a halo of mass m hosts a central galaxy when its mass goes above a threshold mass of m minimum, and can then host satellite galaxies according to a power law governed by these 2 parameters here. So in essence, we assume a lambda-CDM cosmology where we fix the baryon density parameter and the spectral index of the primordial power spectrum, and we free the matter density parameter, the normalization of the power spectrum, and the Hubble constant. We then have the 3 HOD parameters, and now we give some freedom to this beta parameter here, as I'll mention in a moment. Before diving into the actual results, I will just stress again that this are the data obtained using only one single foreground redshift bin, and that we are not combining this probe with any other probes. These are the sole results using the single observer. So having said that, and firstly, we need to talk about this beta parameter here. So according to the galaxy formation model of Lappi and collaborators, this model predicts a value of beta around 3 at the 350 micron detection limit of 29 millijansky. This, along with the fact that this model was found to successfully reproduce the early Herschel counts, motivates the fact that previous works had fixed this beta value to 3. However, we do not only need the behavior of this slope at the detection limit itself, but also in a small neighborhood around it, because we are actually interested in those galaxies that are boosted enough to go over the detection threshold. So we need to give a little room there. How far down should we go in flux so as to ensure that those galaxies can be magnified enough? That's not straightforward because it depends on the magnification, which of course depends on the angular scale. But assuming a typical few percent of magnification, as is typical in large-scale structure, and taking into account the special variation of the instrumental noise of Herschel, we could derive a mean value of beta of around 2.9 with a standard deviation of 0.04. This is our base case, which we will consider as a Gaussian, but we want to gauge the impact of the exact value of this beta in the results that we would obtain. So that's why we ran different tests according to the exact prior distribution information on beta. So here I'm showing the marginalized posterior distributions of all 6 parameters. And in red, you have the case of a quite wide uniform distribution for beta. Green is our base case, and then we have 2 extreme cases with fixed values of 3 and 2.2. So if we focus now on the green case, which is our base case, regarding the HOD distribution, we obtain halo masses that are in perfect agreement with typical values from the literature for the galaxies that we're using. For example, a mean minimum halo mass of 10 to the 11.5 solar masses. And regarding cosmology, although we cannot constrain the Hubble constant with only this single data set at the current stage, we derive a mean value of 0.79 for sigma 8 and a low value of omega matter of around 0.23. Regarding the dependence of these results on the choice of beta, what we can see here is that the parameter that's most affected is sigma 8. Which is not surprising because both parameters control the normalization of the signal in a way. So larger values of the former may induce smaller values of the latter. The omega matter density parameter is interestingly not affected at all by this choice of beta prior information because it mainly controls the large end slope of the cross correlation signal. But what's important from all these figures in a qualitative way is that prior information on beta is crucial because, as you can see in the red case, you can lose any possible constraints on sigma 8 due to the degeneracy with this parameter. Now, if we focus on the beta equal to 3 case, we can compare our results with the previous ones from González Nuevo et al., which I'll show in gray. So the constraining power and the uncertainties in the parameters are, of course, tightened because of the smaller error bars and the larger angular scales. There's an interesting feature in the omega matter sigma 8 plane, although we cannot see it quite well, but in blue, we do not see the typical degeneracy found in usual shear observables between omega matter and sigma 8. And in fact, if we were to have any, we would have one that's orthogonal to it. But there's another interesting thing. The omega matter marginalized distribution is not only narrower, but also very much pushed to lower values. And one reason could be what we can see here on the left. And it is that the new data set seems to be systematically higher above the tendency of the older data set, especially at these largest scales. So the large end behavior is not as steep as one would think with a model, typical lambda CDM model with Planck cosmology. So what could be behind this? Preliminary analysis, we thought, was, okay, let's dissect our signal into the 4 independent fields. And so here we have the cross-correlation measured in G9, G12, G15, and the SGP regions independently. So of course, it's a bit messy, but if you believe me, the thing is that in G9, G12, and SGP, the signal is more or less mostly contained within the error bars. There's, of course, lots of jumps because of statistics, But the idea is the G15 region is systematically higher and actually quite tight in terms of error bars, especially at those larger scales. And so this makes us think that there could be some sample or sampling variance problem within our sample. And before doing further work on this, which we will do, one interesting test was to say, okay, let's exclude this region from our measurements and let's see what the parameter constraints could turn out to be when we do that. So here in olive green, you have the data excluding this G15 region from the measurement. You see, of course, that the large scale fall is not so moderate, it's much steeper, as you can see with the fits to the base case in both cases, the usual data set and the data set without G15. And on the right, you can see the effect this has on our parameters. So omega matter is displaced to larger values around 0.27 when you exclude this G15 region, and sigma 8 is actually tightened and, of course, lowered around 0.72. But qualitatively, which is important here, excluding one of the regions that we had has induced non-negligible changes in our results. So this is something we should look out for. And last but not least, we decided, let's do a joint analysis with galaxy clustering. Let's measure in the angular setting the autocorrelation of foreground galaxies. And let's try to fit it all with the same model. So if you only look at the constraints of the parameters, you see, okay, sigma 8 seems to behave exactly like excluding the G15 region, and omega matter seems to be displaced towards higher values. So in a way, adding the autocorrelation seems to wash away this supposed anomaly with the G15 region. But anyway, the fit is not good, as you can see, because it clearly underestimates the autocorrelation function, especially at smaller and intermediate scales. Among many possible interpretations of this could be the inconsistency that is found in other works between clustering measurements and galaxy-galaxy lensing observables, as shown by the work of, for example, Lotto and collaborators, or Amon and collaborators. But this will, of course, be for future studies. Let's end with a very brief recap of what we've seen. We've seen that magnification bias can induce an excess of background galaxies around foreground galaxies. And this is a very much measurable effect if you choose submillimeter galaxies as your background sample. You can use this as a cosmological probe, which is independent, of course, and complementary to others. And in the setting that I just shown with one wide foreground redshift bin and no combining with other probes, we have 0.23 of omega matter, 0.79 for sigma 8. We do not see any sign of the usual omega matter sigma 8 degeneracy found in other observables. And we've seen that we need prior information on beta if we want clear constraints on parameters. We may be suffering from a sampling variance problem, which we will assess in the future, along with a tomographic analysis or better theoretical models.